Hi, my name is Dr. Wendy Bohan, and I'm an earthquake geologist and science communication specialist for the Incorporated Research Institutions for Seismology, or IRIS. I'm here today to talk to you about earthquakes and the rock cycle. Science is about asking questions. Some of the questions that I ask as an earthquake geologist are, where are the faults? How often are there earthquakes on those faults? How big are those earthquakes? When might the next earthquake occur? And what effect will those earthquakes have on people and infrastructure? Infrastructure is our built environment, our towns, our cities, buildings, roads, that kinds of thing. So let's first start looking at the whole Earth. So the crust of the Earth is the thin outer layer, and it's less than 1% of the Earth's mass. Most of the Earth's mass is made up of the mantle, which is the part in between the crust and the core. So now we're going to look at a map showing the distribution of worldwide earthquakes. All of these little flashes of light are different earthquakes. And if you look really carefully, you can see that they form a pattern. This pattern is showing the outline of the tectonic plates. So the surface of the Earth is covered by that thin skin of rock called the crust. And that crust is broken up into these gigantic puzzle pieces that are moving around very slowly over the surface. Now they can move in different ways and at different speeds. So these arrows are showing the direction that the different plates are moving, and the length of the arrow is showing the relative speed at which they're moving. So the Pacific plate moving really fast, especially when compared to the South American plate, which is moving really slow. So because these plates are moving around in different ways, they can come together in different ways. So first, we're going to look at divergent boundaries marked in green. You can see some up here, along there, all along in here. So divergent boundaries are places where the plates are pulling apart from each other. This is where new crust is being made all the time. Transform boundaries are marked in black. You can see a really important transform boundary right up here along the coast of California. That's the San Andreas Fault. These are places where the plates are sliding past each other. We finally have convergent boundaries marked in pink with these little teeth. These are places where the plates are coming together. These are convergent boundaries where one plate most times is sliding down underneath the other plate. So these different types of boundaries create different kinds of faults. Places that are getting pulled apart or extended create normal faults where one block of rock drops down in relation to the other. If you compress faults or push them together like convergent boundaries, you get reverse faults where one block goes up. And if you shear them or push them sideways, you get strike slip or transform faults. So let's look at that again. Pull it apart, normal faults. One block slides down. Push it together, compression, reverse or thrust faults where one block gets pushed up and over another block. And if you shear it or push it sideways, then you get transform or strike slip faults. So we've talked about faults. What's an earthquake? Okay, as you have these giant tectonic plates moving around, they're creating stress and strain in the rocks, especially along their borders. This stress and strain builds up until the rocks can't take it anymore and they break. This sends energy waves out in all directions, and we feel that as shaking, and that's what we call an earthquake. Stress and strain build up, rocks break, energy waves go out. We feel that as shaking. So earthquakes actually start deep inside the Earth at a place called the hypocenter. The epicenter is the point on the surface of the Earth directly above the hypocenter. Now let's talk a little bit about these waves that are going out in all directions. Every earthquake produces similar kinds of waves. The two we're going to talk about the most today are P waves and S waves. These are body waves that travel through the interior of the Earth. P waves, P is for primary, S is for secondary. P is for primary because that wave travels the fastest. So P waves travel at about 6 kilometers per second through hard rock, whereas S waves travel at about 4 kilometers per second through hard rock. These different waves exhibit different types of motion. P wave is a push-pull wave, where S wave is a shear or a snaky wave. I want you to watch what each one of these little squares of rock is doing when these waves move it. See, pushing and pulling, whereas this one is moving it up and down. Could also be moving it from side to side. So waves travel both across the Earth's surface as surface waves and through the Earth's interior, like the body waves we just talked about. When they encounter things inside the Earth that are different, either a different rock type, a different temperature, something that's more liquid than it is solid, they'll actually change some. And that's how we know what's inside the Earth. It's by looking at the changes to all of these different kinds of waves. So this is actually something that you can look at on our website. This is called Seismic Wave Viewer. You can move the Earth all around and you can look at the waves from real earthquakes to see what happened as they crossed the surface of the Earth and as they traveled through the Earth's interior. So now how do we record these waves? We have something called a seismometer. This is a little house. It's not actually a seismometer, but we're going to see what the seismometer sees. So the earthquake happens. P waves and S waves go through the Earth, and then the surface waves go across the surface of the Earth, and the S waves are slower. Across the top there, you can see the recording of when those waves arrive and what they look like. P wave, the S wave, and then the surface waves. Interestingly, seismometers can record anything that shakes the ground, not just earthquakes. So let's look at some of the other things that seismometers have recorded. So all of these seismograms are the recordings from seismographs, show events recorded at a seismometer in Mount St. Helens. First, elk footsteps. This is crazy, right? This elk was running near a seismic station and we can actually detect its footsteps. Hoofsteps? Footsteps. Next, we're going to see a helicopter landing in the Mount St. Helens crater. So you can see the helicopter lands, and now you can see people walking. See how this is different looking than the last one we saw? The shape of these squiggles help us to identify what caused the squiggle. This is a rockfall in the Mount St. Helens crater. Next, we're going to look at an actual earthquake. So this is an earthquake that happened beneath Mount St. Helens, and earthquakes under volcanoes are very common because as magma and superheated gases move around, they cause the rocks to break and vibrate. Next, we're going to look at an earthquake that happened a little bit farther away. So now you're going to start to differentiate between the P wave and the S wave because they had a little bit of time to spread out. The earthquake, here it goes. And you can see the different seismic waves arriving in Mount St. Helens. So the next one we see is a teleseismic earthquake, or an earthquake that occurred far away from where it was recorded. In this case, this is an earthquake in Chile. P waves and S waves going through the body of the Earth. There's the P wave, the S wave, and now the slower surface waves are arriving. So all of these different squiggles, seismograms, look different. And that's how we know that something is a rockfall or an explosion as compared to an earthquake. We can also detect things like hurricanes. It's pretty amazing. So this is a really simplified version of what a seismometer looks like. It's basically an instrument that's strapped to the ground, and it has a pendulum that's hanging, that's kind of free. That pendulum, when the Earth shakes, the pendulum doesn't move. And that records the motion of the ground as the waves travel by. So let's watch that again. Everything moves but this pendulum. And that records the ground motion. Now, there's lots of different kinds of seismometers. The ones that we use for science are much more complicated and electronic, but you can build them at home. There's things called Lego seismometers. There's slinky seismometers. You can even buy some really inexpensive seismometers, or you can build them out of common household things. Go to iris.edu and type in seismometer, and you can see all of the different types of seismometers that you can build. If you're not much of a builder, you can go on our website. This is called Station Monitor. It's an app and a web page, and you can visit any of our seismic stations anywhere in the world to see real-time seismic data. So there was an earthquake in Alaska. I went in, I clicked on this particular seismic station, and this is what the recording of that seismic station was. Each one of these purple dots is an earthquake. You can click on the purple dot and it will bring up all of those different earthquake waves for you to look at, as well as maps showing you how far away your seismometer is from where that earthquake occurred. Okay, so that's a lot about how we measure earthquakes and what we're looking for. How do earthquakes affect people? Well, one of the main things that we think of when we think of earthquakes is ground shaking, and that can be very hazardous. We're going to watch a video now from Kathmandu. Kathmandu is in Nepal, and in 2015, there was a really big earthquake there. This GPS station was nearby the location of this market, and it recorded the motion of the ground during the earthquake. You can see that reflected by the motion of the people. This is one of the reasons that we say when you feel shaking from an earthquake, you shouldn't try and run. You should drop down to the ground, take cover underneath a sturdy object, and hold on. You can see that it's very, very hard for these people to keep their feet during strong earthquake shaking. Now, it's also important to realize that every earthquake has one magnitude. Magnitude is the amount of energy that's released during the earthquake, the size of the earthquake. But what you experience in terms of earthquake shaking depends largely on where you are. So the magnitude is important. Bigger earthquakes will create more shaking. If you're farther away from the earthquake, you're going to experience less shaking. But there's another important factor that we can explore looking at this shake map. So this is a map showing the shaking that occurred during the magnitude 7.1 Ridgecrest, California earthquake that happened 2 years ago. So this star is the epicenter. Remember, that's the point on the surface of the earth above the hypocenter where the earthquake started. The areas in orange and red are the ones that shook really severely, very violently. And the areas in yellow and green shook less. The areas in blue shook even less. So as we might expect, the area right around the epicenter where the earthquake started experienced very strong shaking. But look at this. There's another area down here that experienced strong shaking. And if you look, there's these little fingers of yellow that extend across the valley. So what is that about? Well, these are areas where there's a lot of soft sand and soils. These are the valleys. And when there's soft sand and soil, the earthquake waves get stuck. So when you're in these areas, you'll shake harder and for a longer period of time. Now, this other map over here is called a Did You Feel It map. Each one of these little squares is a place where people felt the earthquake shaking. And so you can see closer to the earthquake, people felt the shaking more strongly. And as you move farther away from the earthquake, they felt it less strongly. Another thing that can be a real problem during earthquakes is called surface rupture or earthquake rupture. So the earthquake starts underground at the hypocenter and it's caused by the rocks breaking. Sometimes the rocks don't break all the way up to the surface of the earth. Sometimes they stop before they reach the surface. So we feel the earthquake waves, but we can't actually see where exactly the rocks have broken because it's still underground. Unfortunately, in places where it does reach the surface, it can tear buildings apart, just like happened to this cottage during the 2016 Kaikoura earthquake in New Zealand. Now, another earthquake hazard you probably know something about, even if you don't know that you know it. Okay, so have you ever stood on the edge of a lake or a river or a pond or the ocean in the soft sand or soil that's kind of wet and you wiggle your feet? And you know how your feet sink down a little bit? You're basically creating liquefaction. So you shaking your feet is putting waves into the ground, the same way an earthquake put waves into the ground, only on a much smaller scale. So as the earthquake waves travel through the ground in an area that has soft sand and soil and a lot of water, it can push the water up towards the surface. That pushes all the little grains of dirt and sand apart, which causes the surface of the ground to lose strength and turns into kind of like quicksand. So like when you shook your feet and they sank down a little bit, well, when the earthquake shakes the ground, things like houses or cars can also sink down a little bit, sometimes a lot, which is really a problem if that's a house that you lived in. Landslides can also be a big problem. So the 1994 Northridge earthquake caused the coastal bluff under this home in the Pacific Palisades to undergo a landslide, which tore the house in half. So this is a real problem on steep slopes. Now, this is a map that brings it all together. This is from the California Geological Survey, and this is an earthquake hazard map. So all of this region can experience ground shaking. This is Santa Monica down here. Up here is UCLA. So this is like the Hollywood area. These areas in green have soft sand and soil and a high water table. So what hazard is that? Liquefaction. Good. This yellow area with the black in between, this is an area where we know earthquakes have broken the surface of the ground. So this is an area where surface rupture can be a problem. Okay, what about up here in this blue? This is areas with really steep slopes. This is essentially the mountains. So what's the hazard up here? Landslides. So all of this map has different hazards, but depending on where you live, you may have different amounts of risk. So what's the difference between hazard and risk? Hazard is something that has the potential to harm you, like a shark. If you're at the beach and there's a shark in the water, that is a hazard. But if you're not in the water, you're at a low risk from being bitten by that shark. Risk is the likelihood of a hazard causing harm. Now, this is important because people talk a lot about natural disasters. There's not really any such thing as a natural disaster. What you have is a natural hazard like an earthquake or a hurricane that overlaps with a vulnerable system that creates risk and the possibility for disaster. So what's a vulnerable system? It can be lots of different things. It can be buildings or bridges that can't withstand earthquake shaking. It can be people that don't know what to do during a particular hazard. Or it could be, say, like during hurricanes, we tell people they need to evacuate. But what if they can't evacuate? That means that they're a vulnerable population. We've talked a lot about different earthquake hazards and how earthquakes can be bad, but earthquakes can actually be really, really good. And they're really an important part of our planet, maintaining our active planet. They create mountains. They help to create ocean basins. They are very much the thing that is helping our planet to continue to be alive. They're also a very critical part of the rock cycle. So as earthquakes occur over and over again, they change the surface of the earth. And in a lot of places, they create mountains. So let's start here with the mountains. Let's say these mountains have been created along a fault. What's happening to these mountains? There's some snow up here. There's a glacier. So we have some weathering. That could be snow and ice. It can be wind or rain. Weathering can also be little critters, making their burrows. It can be trees digging their roots down into the ground. It can be people digging and building. So we have chemical weathering and mechanical weathering that break the rocks down into smaller pieces, into sediment. Then the sediment is brought down rivers or it's carried by the wind, and it can be deposited in valleys. It can be deposited in the bottoms of rivers, and it can be carried out into the ocean to be deposited. As this sediment is buried by other sediment, it gets compacted. That makes a new kind of rock called a sedimentary rock. A sedimentary rock is made up of pieces of other rocks. Now, let's say that rock gets carried down further into the ground. That's going to cause metamorphism. Metamorphism, you might remember from biology, the whole caterpillar changing into a butterfly, metamorphosis. It's changing into something else. But in the case of rocks, it's due to heat and or pressure. So if you squeeze a rock enough, it becomes a metamorphic rock. Now, if it goes down far enough and you add water into the system, it can melt. That melt underground is called lava. Oh, sorry, it's called magma. When you bring it up to the surface, it's lava. So magma underground, lava on top of the surface of the earth. This magma underground can cool, and that makes an igneous rock. It can also come out at the surface or erupt. That's also an igneous rock. So anything that comes from molten rock and makes a new rock is igneous. So again, we have erosion, weathering, transport, deposition of sediment creates sedimentary rocks. Burial, heat and pressure creates metamorphic rocks. Melting and then solidifying creates igneous rocks. So let's go through the three kinds of rocks again. Classic rock, punk rock, and hard rock. No. What about the rock, Chris Rock, and Kid Rock? Also no. The three kinds of rocks: igneous rocks, sedimentary rocks, and metamorphic rocks. So thanks for joining me today. Again, I am Dr. Wendy Bohan. You can find me on my website. Please go to the IRIS website at www.iris.edu to find all kinds of fun GIFs and animations and cool things. You can also find me on social media at Dr. Wendy Rocks. On TikTok, I'm Dr. Wendy Rocks It. So thanks